Just minutes ago, Mount Etna detonated, and what it spewed out is unlike anything on Earth. This isn't lava. It's a glowing, unknown material pulled from depths scientists said were unreachable. A 140 kilometers per hour pyroclastic surge tore across already charred ground, and lab tests came back with a finding that froze volcanologists. Not basalt, not andesite, nothing in the record. Etna's internal structure now mimics the deadly conditions from 7,200 years ago, right before a flank collapse that spawned a Mediterranean mega-tsunami. Is this a natural alarm bell, or the first sign of a catastrophe building under our feet? Rising more than 3,300 meters above the Sicilian plain, Mount Etna dominates the skyline, a landmark for travelers and a living archive for scientists. Its slopes are etched with the scars of past eruptions, each layer of ash and lava recording a chapter in the island's story. Roman chroniclers wrote of nights when the mountain's fire lit the sea, and in 396 BC, an eruption was said to have halted a Carthaginian army in its tracks, the molten flow blocking their advance. For centuries, local villages have measured time by Etna's moods, the rumble beneath their feet, the sudden plume at dawn, the uneasy quiet that sometimes lingers for months. Guarding this restless giant, the Osservatorio Etneo stands as both sentinel and historian. Its archives stretch back through centuries of observation, from hand-drawn sketches in faded journals to digital seismographs pulsing with data. Each entry is a lesson, some eruptions gentle, feeding vineyards with fertile soil, others violent, reshaping the coastline and scattering communities. UNESCO recognized Etna as a World Heritage Site not only for its beauty, but for the way its constant activity has shaped both science and myth. Yet, for all the drama, Etna's rhythm has become familiar. The cycle repeats, a tremor, a plume, a flow of basaltic lava that cools to black stone. Farmers plant their fields in the volcanic soil, trusting that the mountain's gifts will outweigh its threats. Tourists climb the trails, drawn by the promise of a safe spectacle. Scientists at the observatory track every shift in temperature, every subtle change in gas, building models that, until now, have kept pace with the volcano's habits. This legacy of watchfulness has given Sicily a sense of uneasy confidence. The mountain may roar, but it has always followed rules that experts could read. Etna's past is a ledger of upheaval and recovery, each eruption a reminder that, here, the ground is never truly still. But in the archives, among the records of fire and ash, there is no mention of what has just happened. The baseline has been set. What comes next will test every assumption the watchers have ever held. At precisely 10:03 a.m. on June 2nd, the first orbital alert pinged across the European Space Agency's monitoring network. Copernicus Sentinel-5P, built for atmospheric chemistry, registered an abrupt spike. Sulfur dioxide levels over Etna's summit shot beyond expected values, painting a plume that stretched nearly 6,500 meters above the Sicilian landscape. Sentinel-2, circling overhead, relayed high-resolution images within minutes. A dense, ash-laden column, sharply defined against the morning sky, and a shadow arcing east that rivaled the mountain in scale. Inside the Rome data center, remote sensing analysts watched as the sulfur dioxide cloud thickened and drifted, its intensity mapped pixel by pixel. This was not routine degassing. Automated anomaly filters flagged the episode as the 14th eruption since March, a frequency not seen in decades. The alert protocol triggered a cascade of notifications. INGV volcanologists, civil protection officers, and aviation authorities received simultaneous updates. Meteorologists tracked the plume's path, calculating wind vectors and warning pilots as airspace advisories snapped to orange. Live feeds from the satellites showed the plume's core pulsing with higher reflectance, a signature often linked to denser ash or unexpected particulates. Atmospheric models struggled to keep pace, recalibrating as the plume's chemistry shifted. Sulfur dioxide concentrations well above baseline, volatile ratios hinting at deeper magmatic sources. In the control room, analysts compared the real-time data against Etna's historic records, searching for a match. None appeared. The event's intensity, speed, and chemical fingerprint stood apart from the familiar cycle of strombolian eruptions. With each new orbital pass, the plume's footprint expanded. Ground teams, watching from the observatory and on mobile devices, recognized the signal. This was not an ordinary episode. The satellite confirmation forced a rapid shift from observation to response. Field teams mobilized, equipment was loaded, and emergency protocols activated across Sicily's eastern corridor. The mountain's warning had been delivered from space, clear, quantifiable, and impossible to ignore. The call for a field team went out before the ash had settled. On Etna's southern ridge, the lead volcanologist, Dr. Alessio Romano, tightened the straps on his helmet, radio crackling with warnings from the observatory below. Drones circled overhead, their rotors humming against the wind, relaying live thermal images of a glowing channel snaking through the debris. The air snapped with static. Every few meters, red-blue flashes darted across the surface, flickering like silent lightning against the scorched rock. Romano led his crew upslope, boots crunching over glassy fragments. Each step sent a pulse of vibration through the ground, echoed by distant rumbles from the summit. The team's containment specialist carried a nitrogen canister, its valves checked and rechecked. Protocol demanded nothing less. The sample had to be sealed instantly or risk alteration by the air. Above them, a plume of sulfur drifted east, stinging eyes and throats. The radios buzzed with new data: seismic bursts, temperature spikes, drone feeds showing the substance's glow intensifying by the minute. One technician, glancing at his handheld monitor, muttered about the color spectrum, visible wavelengths spiking where volcanic glass should be dark. The lead signaled a halt. He alone pressed forward, insulated tongs in hand, edging toward the heart of the anomaly. The heat shimmered, distorting the ground into a wavering mirage. He crouched, reached out, and in a single motion, scooped a chunk of the luminous material into the canister. The metal hissed as it met the nitrogen, a brief flash of blue racing across the rim. Sensors on his suit registered a spike, higher than standard basalt, hotter than the air around it. He snapped the seal, checked the indicator, and gave the all clear. The team turned, moving fast, boots leaving shallow prints in the fine ash. Behind them, a second tremor rattled the ridge, loose stones tumbling toward the valley. The drone operator shouted a warning. New fissures opening near the vent, the flow shifting direction. Romano waved the crew back, urgency in every gesture. They reached the extraction point as the helicopter's rotors thundered overhead. The sample, still pulsing with an inner glow, was strapped into the containment cradle. Within minutes, the team was airborne, leaving the mountain's chaos behind. On the ground, the ridge they'd crossed was already changing, the surface pitted and streaked with residual light. The nitrogen canister, now locked in a reinforced case, held what the field chief called the most dangerous puzzle Etna has ever handed us. As the helicopter banked toward Catania, the sample's glow faded behind steel, and the race to understand it began. Inside the Catania laboratory, the sample arrived under armed escort, its steel case still warm to the touch. The lab lead, Dr. Lucia Pompilio, signed off on the transfer, her initials joining a chain of custody logs stretching back to the crater. She moved quickly, gloves snapping as she directed the team. Nitrogen purge, double seal, radiation badge check. Standard protocol, until the containment alarm shrieked through the corridor. Sensors registered a spike in volatile off-gassing the moment the inner seal cracked. A burst of vapor, faintly blue, shimmered in the filtered light. The room's air monitors blinked from green to red as trace oxides flooded the detection grid, levels higher than anything logged in Etna's archives, and with a signature that didn't match basalt, andesite, or any known volcanic phase. Automated shutters slammed down, isolating the chamber. Negative pressure hissed as the sample's glow intensified, casting sharp shadows across the stainless steel. Dr. Pompilio scanned the instrument readouts. Elemental mapping showed transition metals in ratios that defied the lab's database. Peaks clustered where only rare mantle xenoliths, or meteorites, would normally appear. A technician's voice cracked over the intercom. "It's not glass, not tachylite, not anything from the standard suite." The team scrambled, running SEM-EDS and XRD in parallel. Each scan returned the same result: crystalline phases that blurred the line between silicate and oxide, with lattice structures never cataloged in terrestrial eruptions. Raman spectroscopy picked up a spectral emission in the deep blue, an energy band seen before only in deep earth minerals, or in the debris of certain meteorites. The sample's surface temperature refused to drop, hovering above the lab's safety threshold, while the vapor cloud resisted standard filtration. Emergency protocols triggered a full lab lockdown. Within minutes, the corridor filled with the thud of boots and the clipped voices of hazard response staff. Dr. Pompilio faced a decision: transmit the raw data to Rome and risk a global leak, or hold for peer review and risk being accused of burying a planetary anomaly. The debate cut through the lab in whispers and sharp exchanges. Some argued for immediate disclosure. Etna's vent might be tapping zones deeper than any sampled before, rewriting models of Earth's interior. Others warned of reputational risk, the fear of misidentification hanging over every scan. As the sample sat in its isolation cell, the implications grew. If Etna had dredged up material from the mantle's unreachable depths, the event wasn't just a Sicilian crisis. It was a planetary question. The lab's lead, hands trembling for the first time in years, ordered a full suite of isotope and photoluminescence tests. The data would go global, she decided, but not before every protocol was checked, every anomaly confirmed. Outside, the mountain loomed silent, but inside the lab, the emergency lights painted everything in a warning shade of red. The race to understand Etna's message had become a matter of global urgency. Beneath Etna's battered summit, a network of sensors and seismic arrays now probes the mountain's hidden architecture. In the weeks before the eruption, modeling teams at the Osservatorio Etneo and partner institutes began to notice a troubling pattern. Seismic waves slowed as they passed through a broad zone nearly 3 kilometers below the surface. These low-velocity pockets, mapped in color-coded cross-sections, hinted at reservoirs of partial melt, liquid rock accumulating in places where the crust should have been solid. Strain meters buried along the southeast flank recorded a steady uptick in deformation. GPS receivers, accurate to within a few millimeters, showed the ground creeping outward, the slope bulging by as much as 4 centimeters in just 12 days. This rate of uplift, paired with lateral movement, matched the acceleration seen in paleocollapse deposits from Etna's Holocene record. The mountain's eastern side, already dissected by ancient faults, was approaching known stability thresholds. Tomographic models, integrating seismic, gravity, and electromagnetic data, revealed a new conduit, anomalously deep, reaching toward the upper mantle. This structure had not appeared in any previous survey. Its alignment with recent surface fractures and gas vents suggested a direct link between deep magma influx and the rapid deformation now visible at the surface. Slope stability simulations run by the collaborative modeling group showed that the current configuration, with deep recharge and rapid surface strain, could lower the mechanical threshold for collapse. INSAR time series, updated daily, confirmed that deformation was not an isolated pulse, but an ongoing process. The risk was no longer theoretical. The same combination of deep melt, accelerated uplift, and flank movement had presaged Etna's catastrophic collapse 7,200 years ago. For the modelers, the mountain's anatomy was no longer stable or predictable. Each new dataset forced a recalculation, and every recalculation tightened the margin for error. The evidence was clear. Etna's internal changes were now manifesting at the surface, and the consequences could extend far beyond the crater's rim. In Zaffarana Etnea, the morning broke with sirens and the low thrum of helicopters circling overhead. Families gathered in the main piazza, suitcases packed, waiting for updates that never seemed to arrive fast enough. The mayor, Salvatore Russo, strode between clusters of residents, his phone pressed to his ear, relaying the latest from civil protection. His voice, usually steady, now carried the strain of impossible choices. Keep people safe or keep the town moving. The official line was clear. No mass evacuation, no general order to leave. Yet dozens of families left anyway, driving south toward Catania or west into the hills, their WhatsApp groups filling with photos of the glowing plume and questions about school closures. Elderly farmers lingered on their land, unwilling to abandon vines and olive trees that had survived eruptions before. For them, Etna's threat was a risk already priced into every harvest, every season of ash and rain. Shops along Via Roma stayed open, but foot traffic thinned by midday. Tour guides canceled summit treks, and hotel managers fielded frantic calls from would-be guests. By afternoon, bookings had dropped by nearly half, and operators debated whether to refund deposits or gamble that the crisis would pass. The local gelateria, usually packed with tourists, served only a handful of regulars who traded rumors about the mountain's mood. In the town hall, debate flared over a different kind of risk. news had spread of mining companies quietly inquiring about Etna's rare minerals, drawn by rumors of the eruption's mysterious byproducts. The mayor dismissed the idea in a press statement, calling any extraction proposal madness. No mineral is worth a single Sicilian life. Regional agencies echoed his stance, reminding the public that the volcano's slopes are protected by law, off-limits to commercial mining. Still, the prospect of untapped wealth beneath their feet unsettled many, fueling both hope and suspicion. As dusk fell, the mayor stood beneath the shadow of the church, watching the mountain's glow pulse against the sky. He knew that whatever decisions came next would be measured not just in euros or lost bookings, but in the trust and safety of his town. For Zaffarana Etnea, life with Etna meant living with uncertainty, each eruption a test of resilience, and every rumor a spark for new debate. On June 2, 2025, Mount Etna produced a 6,500-meter plume and a 140 kilometers per hour pyroclastic surge. Yet what most stunned scientists was the glowing material. Neither basalt nor any known volcanic mineral, as confirmed by laboratory analysis in Catania. Seismic imaging revealed new low-velocity zones and accelerating deformation, echoing the unstable conditions before Etna's 7,200-year-old flank collapse and the resulting Mediterranean tsunami. Despite exhaustive testing, the substance's true origin and composition remain undetermined. Civil protection agencies have not ordered mass evacuations, but policy debates over mining and public safety continue. As the Osservatorio Etneo's documents show, Etna's behavior has entered uncharted territory, with experts warning that deeper processes are now at play. The evidence is clear. Earth's interior still holds secrets, and even the world's most monitored volcano can deliver the unexpected.